Welcome back to the deep dive. Today, we're scrapping in for one of our most technical journeys yet.
Yeah, this one gets into the weeds.
It really does. For anyone who manages infrastructure or, relies on the people who do, the sources we're diving into are just a goldmine. They are drawn from the sharp end of enterprise virtualization. We're talking about the root causes of major system meltdowns.
And architectural debt, all the fun stuff.
Exactly. But look, we aren't here to study for a certification. Our mission is way more valuable than that. We're here to steal the architectural cheat sheet.
I like that framing.
We are distilling the 10 most crucial configuration secrets, the key diagnosis points that, when you really get them, separate the functional environments from the constant fire drills.
Right.
Think of these as the 10 unbreakable laws of a stable virtual infrastructure.
And that's valuable because the source material, real-world diagnostics, security, performance challenges, it forces you to zero in on a why. It's not just about knowing an error message. You have to understand the architecture, the strict order you have to follow to diagnose something properly.
And that knowledge is the difference between fixing something in 5 minutes
Versus 5 hours or 5 days.
Okay, let's unpack this and let's start literally at the front door. Identity and access. In a massive environment, this is so often the very first thing that goes wrong and triggers panic.
Always.
So picture this scenario. It's a common one. A large group of users, maybe half your engineering team, suddenly can't log into vCenter with their normal corporate credentials. As the admin, there are like 100 things you could check. But what's the single absolute first architectural point you must verify?
Before you check a single password, before you even look at a user group, you have to check the status of Active Directory over LDAP.
Okay, so the connection itself.
The connection itself. What's fascinating here is how often admins forget the architectural hierarchy. vCenter has multiple identity sources. It's got local users, its own internal single sign-on users.
Right.
But if the mass outage is hitting corporate users, the problem almost certainly isn't with vCenter's local setup. The issue is its ability to talk to the central corporate identity server. And LDAP is it's the language, the translation service, that lets vCenter trust those credentials.
So if that link is down or, say, the service account password expired,
then nobody from corporate gets through. It's the highest probability fault. Checking that primary bridge is the 90% solution. It can save you hours of chasing your tail on local settings.
That distinction is just crucial. Okay, let's pivot from a login headache to an immediate catastrophic crisis. This is where it gets really interesting. We need to talk about the dreaded ESXi host failure. The purple screen of death, PSOD.
Yes, the PSOD.
The kernel has crashed, everything is halted, the admin is scrambling. If you want to actually solve this, not just reboot and pray, what specific file holds the smoking gun?
The file you have to grab immediately is the host core dump file. That's it. That's the definitive diagnostic evidence.
Why that file specifically? I mean, what about the host agent logs?
The logs only show you what was happening leading up to the failure. But a PSOD, that signifies a failure so deep, so critical, that the operating system has completely panicked. It's a very low-level event.
Okay.
Think of the core dump file as a snapshot. It's a photograph of the kernel's mind at the precise moment of death. It captures memory, registers, the stack trace, everything. Trying to solve a PSOD without that file is like trying to solve a crime scene after all the evidence has been wiped away.
That makes it perfectly clear. Okay, let's shift now from a catastrophic crash to the slow, agonizing killer of user experience performance, specifically high CPU ready time. Every admin dreads seeing this metric spike. We know it's bad, but what's the biggest misconception about what it's actually telling you?
The misconception is that the VM is stuck, or maybe the physical CPU is busy doing something else. That's not quite it. High CPU ready time means the virtual machine is fully ready to execute instructions. Its task is queued up.
But it's waiting.
It's waiting. The hypervisor scheduler is making it wait for available CPU resources from the host.
I love the analogy for this. It's like the VM is saying, I'm ready, coach, put me in, but the hypervisor is just too busy with other players on the field.
Precisely. It is the one metric that just screams resource constraint. If your ready time is consistently high, it points directly to an overcommitted environment where you've assigned way more virtual CPUs than the physical cores can actually handle.
And wasted CPU cycles are wasted money.
You got it. So let's move from compute constraints to storage, which is usually the next bottleneck. If an admin sees some serious storage performance degradation in a vSAN cluster, what's the one diagnostic tool that gives the most comprehensive, holistic health check?
you'd need something that's purpose-built for that kind of distributed architecture, right? Which means you're turning to the built-in feature, vSAN Skyline Health.
Exactly.
But why is that the definitive starting point? I mean, couldn't I just look at the raw IOPS numbers or latency on a disk?
You could, but you'd be missing the bigger picture. A vSAN cluster is, well, it's incredibly complex. It involves hardware compatibility, specific network traffic between the nodes, disk health, the status of the data objects themselves.
All these moving parts.
So many. Skyline Health is a comprehensive framework that checks all of those layers at the same time. It makes sure you're on the hardware compatibility list. It validates that your data objects are in sync. It verifies the network config. It's basically the central nervous system monitor for your entire vSAN environment.
Makes sense.
And speaking of storage, we really need to talk about failure differentiation. There's a huge high-stakes difference between a temporary connectivity drop and a terminal one. We're talking about permanent device loss, or PDL.
Right, which is much more severe than something like APD, all paths down.
Way more severe. So what's the fundamental characteristic that defines PDL? What makes it different?
It's the communication. PDL is defined by the storage array explicitly telling the ESXi host that the device is no longer available.
That's the key. It's not a silent failure.
No, it's the storage system basically waving a white flag and sending a definitive signal that it's gone.
So why does getting that definitive signal change how the system recovers versus, a simple connection drop?
Because that communication is everything. When a host sees an APD and all paths down, it assumes the link might come back. So it waits. It keeps retrying, hoping to recover the path.
Which takes time.
A lot of time. But when it gets a PDL signal, it knows the device is gone forever. That certainty allows the system to immediately halt I/O to that device and trigger recovery procedures, bypassing all those long timeout periods. It's an immediate terminal failure confirmation. That's a powerful difference. Okay, let's shift focus to resiliency and automation, starting with the network. When you're configuring a virtual switch for redundancy and maybe some load distribution, what teaming policy is the most common standard approach.
The standard workhorse, the one you see almost everywhere, is root based on originating virtual port.
And why that one?
It's the perfect balance of simplicity and functionality. The policy basically binds each virtual port, so each VM's network card, to a single physical uplink.
Okay.
That gives you some inherent load distribution, but it also means that if that one specific uplink fails, the virtual port automatically fails over to another active uplink in the team. It's reliable, it's predictable, and it's not overly complex.
All right, now let's talk high availability, HA. This is the big promise of virtualization, right? A host dies, the VM restarts somewhere else.
That's the promise.
But what if the HA cluster fails to restart a critical VM after a host failure? I'd immediately think, oh, it's the network or maybe a storage issue, but what's the most likely culprit from an HA management perspective?
You're right to suspect those things. But if the HA mechanism itself fails to do the restart, the likely cause is actually insufficient resources in the cluster's admission control settings.
That's fascinating. So the mechanism failed because of a policy, not because of broken hardware.
Exactly. HA admission control exists for one reason: to guarantee that capacity will be there if a host dies. It reserves resources. So if you, the administrator, have overcommitted the cluster beyond what that policy allows,
meaning there isn't actually a guaranteed slot for that failed VM,
then HA will refuse the restart. It's a protection mechanism, really. It's designed to stop you from booting a VM into an environment where it can't function properly. But the result is the HA promise is broken because of a configuration choice.
Check the policy against reality. That's a huge takeaway. Which leads us perfectly into our next automation check: Distributed Resource Scheduler, or DRS. So a DRS cluster isn't balancing workloads. VMs are just sitting heavy on one host, but they're not migrating automatically. Before I dig into host logs or network settings, what's the first thing to check?
This connects right back to the last point. DRS operation is governed by its permissions to act. So you have to verify the cluster automation level settings. DRS can be set to manual, partially automated, or fully automated. If it's on manual, it's only going to give you recommendations. It will never, ever actually perform the vMotion migrations automatically, no matter how unbalanced the workload gets.
So it's a governance issue before it's a physical issue.
100%. If the setting is wrong, you could have the fastest network in the world, and those VMs still won't move an inch.
Check the policy before you check the pipe. I like that. Okay, moving into deployment. An administrator is trying to deploy a template from a content library, and it just keeps failing. Assuming they have the right permissions, what's a common, simple administrative reason for that failure?
This happens all the time, especially in distributed environments. The most common reason is that the content library is not synchronized.
So the data just isn't there.
Or it's only partially there. Content libraries are designed to get templates out to multiple locations, but the system needs to verify them first. If the sync process has failed or it's incomplete, the system can't verify the integrity of the source item. It acts as a hard blocker.
So the library might look okay on the surface, but it's really protecting itself from deploying a corrupt image.
Exactly right.
Okay, finally, let's wrap this up with the highest stakes. Critical security architecture. We're talking about VM encryption. When you enable this feature, what component in the whole architecture is responsible for providing the primary encryption keys?
This is such an important question because a lot of people just assume it's stored somewhere inside vCenter. But that's a huge security anti-pattern. VM encryption requires an external key management server, or KMS, that supports the KMIP protocol.
And why is that external KMS mandatory? Why can't vCenter just hold the key itself?
It's all about the principle of separation of duties. It's vital for security, for compliance. Think of the external KMS as the bank safe. The vCenter system is only given an encrypted receipt, a pointer to the key.
Okay.
The KMS holds the actual master key. This ensures that even if an attacker completely compromises your vCenter or an ESXi host, they only get encrypted references. They never get the primary key needed to decrypt your data. It maintains the cryptographic integrity of the whole system.
And that's a wrap on our deep dive into the foundational failure points of enterprise virtualization. We'll see you next time.